this thing, and the title is sort of in two parts. So there's this thing Effect-theoretic and this thing Reconstruction of quantum theory. Now I know this is a category theory conference, so people are not necessarily familiar with quantum theory. I will keep it very light on this part, and I will focus a bit more on this part, Effect-theoretic. And what I mean by that is I'm going to use structure and assumptions from Effectus theory. Now I'm actually not sure how widely known Effectus theory is, and so I would kind of like to see a show of hands who has heard the term Effectus theory before.
Heard or understood?
Heard. Who has understood part of it?
I'm making
Okay. Okay, the heard is actually more than I expected, so that's quite nice. Yeah, so like I'm going to talk about that a bit later. First, going to explain a bit about like what this reconstruction quantum theory business kind of means and what the motivation is for this work and what I'm doing. Okay, so the question I was interested in is why quantum theory? And what I mean by that is we have a universe that we live in, and it has physical rules. And these physical rules happen to be described by something we call quantum theory. And like the mathematical description of that is quite complex. Like you have these things called C-star algebras, and like these are like operator algebras and have all these axioms and things attached to it, and states and density matrices, and you have like complete positive maps that change stuff around, and like there's all this mathematical stuff, and like it's really unclear why we would have this described nature so well. And like, and also this, like the way quantum theory was developed, like we had all these like experiments and results, and it was sort of like fit together, and we had this model, and it was like, okay, why do we have this model? We don't know. So a way to start answering this question of why we have this model of like C-star algebras or Hilbert spaces and all this stuff to describe nature is to find some sensible physical requirements from which we can derive all the structure. And like the canonical example of this is like Einstein in like 1906 or so, I think, where like he just says like, okay, what if I assume that the physical laws everywhere are the same and the speed of light is constant? And then he just goes back to his armchair. He just sits, he thinks, and he's like, oh yeah, Lorentzian space-time and stuff. Like he's deriving all of that from like a few principles, and that's kind of like the goal here, to do that for quantum theory. This thing doesn't really work well, does it? Yeah, and then if we're successful with this regard, then we can sort of say quantum theory, like the mathematical quantum theory, described nature because it couldn't have been any other way without these physical requirements not holding, so that nature would be much weirder than that. Okay? Okay, this sucks. So I'm definitely not the first to ask this question, and like the history of trying to find principles to derive quantum theory goes back all the way to like the 30s with von Neumann and yeah, like all these original folks from quantum theory. But like the modern approach to it started in 2001 by Lucien Hardy, and he found this like reconstruction. He found 5 principles, and like he reconstructed. I think it was just matrix algebras or just Hilbert spaces and unitary maps or something. And like he had found 5 actions, but they're still like really like they're not super nice or super intuitive. Like they're quite mathematically stated. 2007, Barrett used kind of the framework that Hardy used and defined something called a generalized probabilistic theory. And this is kind of, in a way, the most general physical framework you can imagine. So it sort of models like what an experimenter can do in a lab. So it says like I can prepare a system, I can do a transformation on the system, I can do a measurement, and they should give me a probability of like the success of doing all these things together. Categorically, you can say it's a symmetric monoidal category enriched in finite dimensional ordered vector spaces over the real numbers. So like that's the categorical thing.
This was announced in the 70s.
Okay, well, it had this name since 2007, as far as I know.
Huh?
It had this name since 2007. Like,
Yeah, well,
yeah.
Ludwig built this framework somewhere in the 1970s.
All right, cool, nice. Then like this other reconstruction by De Kiech, I don't know how to pronounce it, Bruckner. And like they had less actions, but they were still very strong, but they were sort of more nicer intuitively. And they introduced this thing called local tomography, which is a very useful thing, and I'm going to come back to that later. And then in 2011, I think this is currently the most widely known reconstruction, and they give things that say something about like the informational properties of quantum systems. So they say like, if I have a physical theory which like the information in these systems behaves in this particular manner, then it must be quantum theory. And yeah, there's lots of others since then. I did a kind of a count, and like I think since 2000, like in the last 15 years, there's like 20 or 30 reconstructions of this regard. And like I would say, like, okay, so why would we do another one? And as I say, I still think all of them aren't like super nice. They're still not the definitive answer to this question of like what are the physical principles behind quantum theory. What I want to do in this talk is I want to do something that's more inspired by category theory, in particular effectus theory, and just use principles from effectus theory that were derived, that they were like sort of thought of not to find a reconstruction of quantum theory, but just like, oh, this is interesting structure, and I want to use that structure to like, see that this is enough to get back quantum theory. And the principles, or like the things I will ask to exist, have to do with pure maps, and it's basically saying if I have some physical theory where like there is a thing of pure maps and the pure maps behave well, and behave well will turn out to be it's a Degger category and it has some nice isometries in it and stuff, then it must be quantum theory. Okay, so that's kind of the motivation for what I'm going to do next. Yeah, and like if you're doing a reconstruction, you sort of need a framework. So like for Einstein, for instance, his framework was space-time. Like you had like events in like this four-dimensional thing. And yeah, like my framework is going to be like effectus theory. And effectus theory was developed in Nijmegen by Bart Jacobs, Kenta Cho, and the Westermann brothers, Bas and Bram. And yeah, there's this huge paper, Introduction to Effectus Theory, which is very mathematically heavy. If you want to learn more after this talk about effectus theory, I would suggest reading Bas's PhD thesis, or at least like the second part of it, which sort of gets a more modern introduction to effectus theory. And yeah, like an effectus is basically a generalized probabilistic theory, and generalized in the sense that instead of real numbers, you allow any effect monoid, and vector space are replaced by effect algebras. And like I'm going to explain what those things are. But first, a definition. So an effectus is a category which has finite coproducts and a final object I, such that two conditions are satisfied. The first condition is that these two diagrams are pullbacks for all objects x and y in a category. And the second condition is that we have these two maps and they are jointly monic. Now, if you're anything like me, this definition doesn't mean anything at all. It's just like some properties. And like, don't worry about this. I'm just showing it to show you that like there is a clean categorical formulation of what an effectus is, and like forget about this for the rest of the talk. First, examples of what are effectuses. Sets, the category of sets and functions, is a effectus, and more generally, any topos is a effectus. So I'm told. Do not ask me any questions about this because I have no idea why or how. The Kleisty category of the distribution monads, otherwise known as classical probability theory, is a effectus. In particular, any category which has byproducts, and if it has suitable discard maps, I can look at the causal maps in this category, and those form an effectus. So it's a very general kind of construction. There is this thing called an ordered unit space, and this is a ordered vector space, a real vector space, which has like the order satisfies some properties. And if I take the opposite of this category, then I get a effectus. In particular, any causal general probabilistic theory is also an effectus. So this generalizes the concept of a generalized probabilistic theory. Also, as a specific example of this, the opposite category of von Neumann algebras. If you don't know what von Neumann algebras are, if you know what a matrix algebra is, so like just a set of matrices of complex numbers, and you generalize that to infinite dimensions and stuff, and you make a nice category out of it, you get von Neumann algebras. Or you get C-star algebras, but the nicer categories von Neumann algebras. So these are all examples of this thing. You might be surprised to see like you need the opposite of this category. The reason for this is that the effectus language deals with state transformers, and like these categories kind of want to deal with predicate transformers. So if you're from a computer science background, like state performance, predicate transformers go in the wrong direction. If you're from a physics background, it's like the Schrödinger picture versus the Heisenberg picture. So like you have like different ways of viewing these things, and that's why we need the opposite of a category. So there are some basic definitions in effectus. In particular, there's sort of like the Kleisty way of like having the maybe monad, and we can construct partial maps in effectus. I can give you states, and states are morphisms that go from the trivial object to a thing x. And I have a thing called effects, and they are kind of like the partial maps back into this trivial object. And if I compose a state with an effect, I get a map that lives here, and this I call these scalars, because like the intuition here is that if I prepare a state and then I apply an effect to it, an effect is a measurement, I get a probability out. So these scalars are my probabilities in this theory, and like they don't have to be real numbers; they can be something more general. And the thing they can be is well, the states form an abstract convex set, and the effects form an effect algebra, and I'm going to explain what that is. And basically the partial maps, they preserve all the structure of like the abstract convex set and the effect algebra. And this definition that we just saw is basically kind of the minimal requirements to get this out. And it's actually a very long way to get from this definition with pullbacks and jointly monic things to get all this stuff. But like, yeah, like it's chosen to make this stuff work. Okay. So an effect algebra is a set which has a 0 and 1, and then partial addition. And partial addition, I mean that sometimes x plus y is defined, but when x plus y is defined, also y plus x is defined, and like these are equal because it's commutative, and the same kind of condition with associativity. And then it has an involution operation, and this is a kind of like interpreted as like 1 minus x. So like if I do x plus like x perp, I call this thing perp for perpendicular and stuff, then it should be equal to 1. And yeah, this is what an effect algebra is. And the obvious example of this is the unit interval in the real numbers. And I just define x plus y when x plus y is smaller than 1, and the perp is just 1 minus x. More generally, any Boolean algebra forms an effect algebra. If I have an ordered vector space, I can make any interval, and this is also an effect algebra. In particular, if I have a C-star algebra and I can take the set of elements that are positive and smaller than the identity, and those also form an effect algebra. And yes?
Could you just intuitively, why do you need the involution to make this an effective effect algebra in terms of the
so if you don't have the involution, then it is something called a partial commutative monoid or something slightly more general. It's a weaker structure, like you have more of them. Like,
I was just wondering, in the context of causality, I guess I'm crossing ideas here, but it's something to do with causality.
Okay, so if you're thinking about generalized probabilistic theories, having this thing is kind of saying that like that if I have some effect, I can always make it into a measurement, because then I have the two elements, and this thing says the measurement had a successful effect, and this thing says it did not have successful effect. So it's kind of like you complement the measurement. You say like, if I measure x, I say like, is x true? And then x complements like saying, is x false? Like that's kind of the intuition that I have there.
So it's like not.
It's like not, yeah. And like in the Boolean algebra, it's yeah. I don't know, it's a bit yeah. Anyway, like yeah, if you can just think of this about like an interval in like an ordered vector space. Like if you take like the 0-1 unit interval and you just take n copies of it, like, and you have all the pointwise operations. There's also an effect algebra, for instance. So that's kind of the intuition you can have there. Oh, and effect algebra, and this is also a reason to have this thing. They have an order defined on them, where like x is smaller than y. If I can find some element z, such that if I add z to x, I get y. And like this reproduces a standard order on like 0-1, for instance. Okay. So now a definition that I find more workable, and this calls like a baby effectus, or like I call them in the paper, is an effect theory. And this kind of gets you like the intuition of like what is important in effectus, for me at least, is it's just a category which has some designated object I, such that the morphisms from A to I form an effect algebra, and all other morphisms preserve the structure, so they preserve the addition when it exists. So I'm thinking kind of here like as like the partial maps in an effectus, but like so.
From A to I plus I?
No, so the definition I just gave is like the definition of total maps in effectus. I'm now thinking about sort of the Kleist category of it, so like the partial maps. Yeah. So this is basically the only thing I want you to remember for like the definition of effectus. This is the only thing that's important for us now. So like I don't need coproducts or all this pullbacks and stuff. Like this is sufficient. Or well, it's sufficient. It's like the basic framework, and then we're gonna lay stuff on top of that. Let's see how much I'm on time. Okay. So there's two like standard notions in effectus theory that are very useful, because like this is such a basic structure, you cannot define a lot of things. So you need to do something with these effects, because that's the only thing you know something about. So there's a thing I call a compression, and a compression is a map which goes from like an object like this, which I call sort of like the compression object for this effect Q. And it has this property that it maps the effect 1 to the same thing as it maps the effect Q. And the intuition here is that it throws away Q perp, so it sends Q perp to 0. And like, so it sort of compresses your system onto the part where Q, if you view Q as a predicate, where Q is true, and it throws away the rest. And it has this universal property that it is final with this property. So if I have any other map into A, which has the same property, there's a unique arrow that makes this thing commute. So it's just a final object in sort of category.
Sorry, the notation.
Yes.
What do you mean by A? Like how do I read the domain of pi? Notationally, I don't understand the notation.
The domain?
Like is a map pi q from.
Yeah, so that's just a notation for an object. This is just an object in the category. That's just
okay,
yeah. Yeah, sorry. Yeah.
I thought it meant something.
No, it's just an object. What we also have is a filter, and a filter is like goes from A to another object, just label as object AQ, and it satisfies this property. And again, like I want to interpret this as also a way of filtering my system that like Q is true. So like if you want to view this operationally, sort of like post-selecting for the predicate Q to be true, and like being on the system where this is possible. And it also has a universal property, namely it is initial with this property, and that's this diagram. And if you think these things look kind of dual, it's that is kind of true, and I'll make this a bit more precise later on, namely a bit on like the next slide. I know you like this is a category theory conference, so people like adjunctions and stuff. So I'm just going to show this slide. It's possible to make this other category predicates of C. Predicates are like a different name for effects in effects theory. And we have this obvious forgetful functor that goes back to C. And there's like two ways to embed C in the predicates, namely like just attach a 0 effect to every object, attach a 1 effect. And these are left adjoint and right adjoint. And then then you have these things called quotient and comprehension. And a quotient is basically a filter, like what I just described. And a comprehension is basically a compression. So like these things I just showed on the previous slide, they are canonical in the sense that they form like a left adjoint here and a right adjoint there. Just thought I would show this to sort of like appease the categoryness of this conference. Yeah, if you want to learn more, like there's these references. It's not important for like what I want to do. So the example of like what I want to talk about is like this gets closer to what I mean by category theory. So like if I have the matrices or the complex numbers, and I'm taking the opposite category here again, and they're just matrices that preserve the positivity of elements. So I'm talking about here if I have a positive definite matrix, I want my maps to preserve this positive definiteness, and it should map 1 to something below 1, and 1 is the identity matrix. And then the effects, you can show that they correspond to elements of this algebra which lie between 0 and 1. And I can always diagonalize an effect in terms of projections. And then I can define the ceiling of Q, which is the smallest projection that's above Q. And I can define the floor, which is the largest projection below Q. And then the compressions and filters are basically, the compression is like a projection map into this smaller space, and the filter is this map, which some people, if you're from physics background, might know is like the Luders map or a measurement map, something like that, or like a post-selection for Q. And yeah, that's kind of the intuition between like compressions and filters, what they mean in like quantum theory. Okay. We need one more definition, and then like we're done, like concept-wise. So an image in an effectus, in an effect theory or an effectus, is a smallest effect. So this Q perp F is 0, or you can say like a smallest effect that Q after F is the same as 1 after F. And like it's kind of like if you think about kernels and cokernels, like this is kind of like it's related to that. And images in the general effectus, they don't have to exist, but like I'm going to assume like in effects I care about that they will exist. Yeah, then we can define what it means for an effect to be sharp. And like sharpness, intuition there is like in quantum theory there would be the projections. And I should say an effect is sharp if there's an image of some map. Like there is some map and this thing is the image of it. And like now we can relate all these like sort of new definitions in effects theory to something that more people might have heard of, which is that like if I have an effect theory and it has images, and every sharp effect has a compression and a filter, that's if and only if the category has all kernels and cokernels. So if you've heard of kernels and cokernels, these are related in this way to having compressions, filters, and images. And in fact, you can say that compressions are kernels, like they have the universal property of a kernel. And if you have a filter for a sharp effect, it has the universal property of a cokernel. So in this sense, a filter is a fuzzy cokernel. Like it is also a universal property, but then also for non-sharp effects. Okay. And then we can give the definition of what I said. Like I want to say things about pure maps. And I'm going to give this definition, which might seem a bit weird at first, but like a map F is pure if I can find a filter psi and a compression pi, such that F is like a composition in this particular order. So it's first a filter and then a compression. My motivation for this is that if I take this definition in like this category of complex matrices, which is kind of like quantum theory, then I get exactly these things which are called like Krauss rank 1 operators, but like they're like if you're talking about like which maps should be pure in quantum theory, you're kind of thinking about these maps. So this kind of definition that like this gets you like an abstract definition of purity that corresponds with the right definition in quantum theory. Like right definition is also debatable, but like yeah. And yeah, from the definition I gave, it's not clear that pure maps are closed on the composition because I have this very particular order of things. And like if I compose two pure maps in this form, it's not necessarily clear that like I can reduce it back to something which is just this thing. So like I need to assume this additional structure that like these pure maps are actually closed on the composition. But like this is true like in these matrices things. And also as you can see, there's an obvious dagger on these pure maps in mat of C. Namely, I can just dagger the v's and I put them in a different order, and I have a dagger of this map. So I'm going to take this as intuition, and I'm going to start defining like a nice effectus, like an effectus that has like the right structure I want. So first of all, I need all images. Yeah, I need all images, and when Q is sharp, I need Q perp to be sharp. And this is kind of unfortunate that like this is not that doesn't happen automatically, but yeah, maybe you can prove it, but I don't know. Then I say all effects have filters and compressions, and the pure maps form a dagger category, which is basically like the previous slide, the intuition you get from quantum theory. And there's two more conditions on this dagger category, which is that if I have a compression for a sharp effect, then I need its dagger to be a filter. And this is kind of like this duality between the compressions and the filters. And like if you think about them as like kernels and cokernels, it's a natural condition to have on like a category. And a compression for a sharp Q must be an isometry. So like if I do the dagger after a compression, it must be identity. And again, if you're thinking about like a dagger kernel category or something, this also makes sense. Okay, so examples of such nice effectuses. Again, a classical probability theory. The category for phenomenal algebras with these very particular maps between them. This is kind of my example of infinite dimensional quantum theory. Also the category is real C-star algebra, so kind of like quantum theory over real numbers instead of complex numbers. And this thing called Euclidean Jordan algebras, which I want to say about a bit more. So a Jordan algebra is a real Hilbert space that's the inner product, and it has a commutative product on it satisfying this identity. And this identity is sort of a weaker form of associativity. And the motivation for this definition, so it also has an order on it defined by the elements that are squares. And the motivation for this is if you take the self-adjoint matrices over the field of real numbers, complex numbers, or quaternions, and you define this product in this way of like AB plus BA, then it forms a Jordan algebra. And this is how von Neumann, Wigner, and Jordan in the 30s, they defined it as sort of like a generalization of quantum theory. Usually when I talk about Jordan algebras, like people are like I don't care about this thing. And then usually I go on and I explain like why you should care about these things. So yeah, like why they are cool, like this will come in 2 slides. So first I want to say to bring effect theory, which is quite abstract, to something more concrete physically. So I'm going to define effect theory and say it's operational when the scalars are just real numbers and the states order separate the effects. And this kind of means I have enough states that the order on the effects gets like I can find this order by just considering the effect of states on it and like all these things. And what you get then is that these things must form finite dimensional, must form vector spaces. And I just ask these vector spaces to be finite dimensional, and then the sets of states form like sets of functionals on this vector space. So I ask that this set is actually closed in like the metric on it. These are all standard assumptions in like a general probabilistic theory. And so this is kind of like my way of getting from an effect theory to a generalized probabilistic theory. And there's this final technical condition which kind of says that if a system acts like a trivial system, it must be trivial. And so it's kind of like a generalized probabilistic theory. And then like the main theorem, like my first main theorem, is that like if I have a operational pure effect theory, so a nice effectus which is operational, then it's basically a Jordan algebra. So I have this functor which maps effects isomorphically to the effects of a Jordan algebra. And this functor is faithful if I have enough effects to separate all the maps in my category. So it's kind of like saying like an operational pure effect theory is a Euclidean Jordan algebra. This is kind of like my reason for like why you should care at least a little bit about Jordan algebras is like you get these very nice intuitive axioms about like a Dagger category of pure maps and you get Jordan algebras out. And then you need to go from Jordan algebras to quantum theory, and this is quite easy to do because Jordan algebras don't have a tensor product, so I just add a tensor product in. So I just define a effect theory to be monoidal when it is monoidal itself, and this designated optic I is the monoidal unit and like tensor preserved addition. And then also for a pure effect theory, I require that the pure maps they're also a monoidal category. And then I can extend this theorem and I get a functor into the category of real or complex C-star algebras. So it's kind of these two possibilities that you get. But if I say that the effect separated maps, then you only get C-star algebras that are over the complex numbers, because real numbers, they don't satisfy local tomography, if you know what that means. So from these assumptions, I basically get quantum theory back. So I don't have much time. Yeah. Yes, this is the last slide. So what we did is I found a definition of purity motivated through effectus theory. Then we show that like if you make an operational definition of it and you have these purity assumptions, you get Jordan algebras. If you add a tensor product, you get C-star algebras, so quantum theory. For future work, I want to see like can we get rid of some of these conditions? How much can we actually do without going to the operational settings? How much structure do we get there? Can we get Jordan algebras over different fields? Like if I don't have real numbers but have some other weird field, can I get Jordan algebras there? And can we do this in infinite dimensions? If I adopt the finite dimensional constraint, and I'm almost there. So that's kind of like what happens soon. Some advertisements, and thank you for your attention.
It's not quick though. I'm going to betray my physics origins
and I'll be talking about quantum programming, inductive data types again, and it's like a few more buzzwords in the title. So causality, a lot of people are talking about causality now, but this is very important. I didn't include it just to be cool. Okay, so inductive data types again, super important. If you don't have inductive data types in your programming language, then what's the point of living? So.